Happy Friday, it's May 8th, and today on the live stream, I'll be sitting down for a chat with Andy Ferlitsch to talk about automatic machine learning. Here we go. Hello and welcome to the live stream on Adventures in the Cloud, where we explore new and interesting ideas, concepts, tools in the cloud. My name is Yufeng Guo, and today I am delighted to be joined by Andy Ferlitsch. He's part of the Google Cloud AI Developer Relations team, and he focuses on deep learning and computer vision. How are you doing today, Andy?
Oh, I'm doing just great. I'm here working from home in Portland, Oregon, and I'm happy to be part of your podcast here and tell your audience about automatic machine learning.
Awesome. Thanks so much for coming on. I know viewers are really excited to learn more about the developments in automated and automatic machine learning. It's been a real hot kind of topic these days, and there's so much going on that it's really hard to keep track of. And so I understand you've kind of prepared a little presentation for us that we can kind of work off of and chat about. So with that, let's get started. And I also want to let people know, be sure you can check in on the live chat and ask questions there, discuss what we're talking about, and we'll definitely be monitoring that as we go along. So with that, I'm going to switch over to our slides view and let us get started. All right, Andy, it's all you.
Okay.
All right.
Okay. Well, first I just want to start with explaining the difference between AutoML and automatic machine learning. Lots of people have heard of AutoML, and there's two things. One is that's actually a product name for a Google Cloud product. Okay. And the other place you see the phrase AutoML was in that really groundbreaking paper Google published a few years ago about how it discovered NASNet, and it put the phrase AutoML in the title. But they're really not the same thing as automatic machine learning. That AutoML is just a subset of a much larger category. And that's what we're going to talk about today, is that much larger category.
Awesome. Yeah. No, thank you for clarifying that, in terms of it being this bigger thing than perhaps I think most people necessarily realize, that there's more to it, right? Not just that one product, not just, as you said, NASNet, which is short for Neural Architecture Search, NAS.
Okay. Yeah. So to many, sort of the granddaddy or sort of the simplest form of automatic learning is transfer learning. And I think the majority of you out there are familiar with this. So it's the idea of taking a pre-trained model that's been trained on one data set and being able to sort of reuse it on another data set. And the assumption is that the new data set is very similar to the other one that was been trained on. For example, let's say you trained a model on fruits, and now you wanted to train a new model on vegetables. It's probable that what the features learned by the other model are reusable in the new model. So if you look at this slide, we kind of break the model into what we call this bottom half. That's your stem convolution group, and then all your convolutional groups just before you get into, we're talking about image classification, the classifier. Okay. And at that very end, you have what's called the bottleneck layer. That's where you take the final feature maps, flatten it into a 1D vector, and then you go into a dense layer. Now, I use the word task here because models could be learning any task. It could be object detection, classification, and so forth. And the idea is you're going to tear off that task layer, and you're going to put in a new one, a replacement one, and train your model, just simply retrain just the new task, reusing all the weights above that in the model. And that's kind of what we call the feature learning part of it. Sometimes we're a little bit further away. The two data sets are a little bit more distinct. So we might even tear off more of the model and retrain and add new parts. For example, the bottleneck layer is a common one. People also tear off and put in their own bottleneck
Right.
layer.
Awesome. Yeah, and I guess with transfer learning, being so common and not just being relevant here, we're seeing an example that it seems to be fairly tailored toward ConvNets and computer vision applications. But we're also, I think, we've seen applications of transfer learning beyond just computer vision, right? In deep learning spaces around kind of audio and natural language and things like that you can use this technique.
Well, definitely in natural language with things like BERT and so forth. You see a lot of transfer learning being used.
Cool. Okay, so from here, should we move on to the next topic here?
Yeah.
Awesome.
Next slide. Okay, so another area of sort of automatic learning is really is what are the initial weights to my model when I train it? So, over time we've discovered, so let's start simple. When I got a model, they all have to, every weight has to start with some value. And what is that value? Now, if I set them all to the same, say 0 or 1, what would happen is all the weights would be updated uniformly. So you'd have symmetry. So it'd be the same as only having one node. So that initialization, all the weights have to be different. And we tend to do that from a random distribution, like a He normal distribution. But what we have found is some draws from that distribution are better than other draws. That is, some draws will lead to good convergence and accuracy, and other ones won't. And the idea is, how do you get that good draw? Well, one way of doing it was became very popular in 2019 was the lottery hypothesis. And the way it's actually implemented is that you would have your reference model is uninitialized, and you got your random distribution, and you're going to take a whole bunch of instances of it, 10, 20, 100, it doesn't matter. Each one of them is going to have a different draw. Okay. And you're going to pre-train them with a really tiny learning rate for a very short amount of time. So you're not looking at things like accuracy or validation. You're looking at the training loss, how it starts to drop. And so you're going to run all those, and then you're going to pick out of that set which one you think has the best dropping in the training loss. And you're going to say, that's the one that's going to be my winning ticket. That's the initialization I want to start.
Interesting. So it's kind of like you're trying to pick in that landscape of in your loss landscape, so to speak, where you can get kind of a nice fast starting initial descent phase, so that you can kind of kickstart things and not be kind of wandering around on the plains, hoping that you might, or maybe take a long time before you find a suitable region, and you can just start there instead. Interesting.
Yeah, and it's really important. Think about, early on, one of the things you do is hyperparameter tuning, and you might try different trainings. Well, if you got a bad weight initialization, what good is the hyperparameter tuning, right? So actually, it's very important. There's several different techniques, and I'll cover another one. Before we even do our hyperparameter tuning, we want to make sure we got a good weight initialization.
Yeah, no, that totally makes sense. That's really neat. And how does this then tie into automatic machine learning? Like, is this going to be something that you would include in like sort of a pipeline of steps that you would prepend it?
Part of the pipeline.
Cool.
Right. So instead of you manually trying to pick, a weight initialization, the system would automatically create instances, pick a tiny learning rate and a number of epochs, run them probably in a distributed manner, and automatically observe the training loss and make a decision which one of those instances is it. That's the winning ticket. That's the one that's going to pull out and push it to the next point in the training pipeline.
And we have a comment from the live stream comment saying that this kind of sounds like a bit like the evolutionary model, right, where the initial weights are seeked out by generation of samples, but like I guess in this case, we just have one generation. There's no kind of further
There's,
evolution.
I mean, evolutionary would make an assumption that somehow I pick like the two best
Mm-hmm.
ones, and somehow I pick one half of one and one half of the
Right.
other, combine them together, and then try that. But yeah, so this is, as you say, is just one
Got
generation.
it.
Lots of siblings.
Yes, many, many siblings.
Right. Okay, so next slide. So this is a different approach to weight
Mm-hmm.
initialization. We refer to it as warm-up. So a lot of you may have heard of warm-up training. And what does that mean? Well, this kind of goes different than the lottery hypothesis. This assumes that the sort of, as you go deeper in a neural network and all those extra layers, one of the things they do is they provide stability to the what's called the bottom, or actually the initial layers, to have a good weight initialization. That is, the model learns what the best weight initialization is. So what we do in warm-up is we take a reference model. We're going to take just any random draw from our random
Mm-hmm.
distribution, but we're going to start with a really tiny learning rate and do some pre-training, just short spurts of it. And we're going to gradually increase the learning rate. And we're trying to get those weights to shift around just a little at a time. And the assumption is that it's going to learn that best initialization and become what we say is numerically stable. And now we're ready to do what actually would be next, our hyperparameter tuning, and then our full training.
So, how is it that it's learning the initial weights if there's only one model instance being kind of is it the same model instance that's being upgraded or
Yeah, it's the
updated?
same model. Let's look at the lottery. In the lottery, all of them are working, training on that same tiny
Okay.
learning rate.
Yeah, exactly.
Okay. Here we take one and we're actually varying the learning rate. And we're sort of, by a little bit increasing each time, we're sort of getting those weights to
Yeah,
shift
more and more.
more and
Yeah,
more in a better direction.
gotcha.
And so the focus is not the model learning the
Mm-hmm.
data, but the model learning the best weight initialization.
Gotcha. Cool.
And that's the warm-up principle.
All right, so now we're on
Right?
to
So,
translational and scale invariance. Some
variance.
some
Okay, yeah. And
data
many of you are
manipulation. Yeah.
already familiar with this, with image
Mm-hmm.
augmentation. And you ask yourself, what's the purpose of image augmentation? Um, in anything that's dealing with images, whether it's classification, object localization, object detection, image segmentation, you want it that it doesn't matter where in the image the
Right.
object is. And that's your translational invariance. And you don't care what perspective or scale it's
Yep.
at. And that's your scale invariance. And what you'd rather not do is have to get vast number of images of different scale and different locations. How can I take my existing data set and train the model to be translational and scale invariance? And that's what the image augmentation part is in the pipeline. It automatically produces that for the training. So in its simplicity, you take your training data, you're going to grab a batch,
Mm-hmm.
okay? Let's say 16 images. And then you're going to randomly choose a subset of them. Typically it's one half. So let's say 8. And then you're going to do some random transformation to that. And it's the modified batch that the model learns off of. And by doing so, the model automatically learns translational scale invariance with you not having to provide extra data that's
Right.
needed.
Yeah, this is a really powerful tool, and because of all the ways that you can modify it, like different tiers of modifications, right? Like you can scale it a little bit, scale it a little bit more, and so there's or like translate it this way, this way, this way, this way, and you end up, and it's all multiplicative, right? And I've also seen ones with images where they'll change the brightness of the color, the image, the contrast, and things like that, and cause all sorts of and so you multiply all that together and you can very easily
Yeah.
10x or
Yeah.
20, 50x your data set, effective data set size.
Yeah. I'm going to talk about, but changing the brightness, color, and all that falls
Oh,
in
does
another
it?
area
Oh,
called
okay.
contrastive. Yeah, contrastive learning.
Nice. All right. So we'll get to that. Don't want to get too far ahead of ourselves.
Okay, so next slide.
Here we have
Okay.
essential. That's
So,
really cool.
so the next sort of important thing to know is today when we talk about training a model, we use this phrase essential feature learning. We kind of beat it in. So if you go back a little bit in time, one would say is a model was learning the
Mm-hmm.
data. And the problem with learning the data was
Right.
memorization. It would learn to memorize the data and not be able to generalize to the test or holdout set. And so we came up with all different ways to prevent that overfitting, like through
Mm-hmm.
regularization. Okay. And then, so instead of learning the data, we kind of moved on to learning the data set.
Right.
Okay, instead of the
Uh-huh.
data. So you're not memorizing. And so that the model could generalize to the test or holdout data. Now, the thing here is the assumption is the test and holdout data has the same data distribution as what you trained on. Okay. The reality is no matter how perfect my training distribution is, when I deploy my models into the real world, except for ideal situations, they're probably going to see some
Yeah.
shift in that distribution. We call it data
Mm-hmm.
drift. And so we want our models to be able to generalize to that shift in the distribution it does not know without being directly, without having a training data to do that. So in that case, what we're saying is we rather have the model simply learn the essential features. And if it learns the essential features, it can generalize to shifts in the data distribution. So one way we do it is with synthetic data. So here is an example I show of cars. So there's a lot of generators, synthetic data generators
Yeah.
nowadays, like the Unity
Right.
engine. Okay. So it can automatically generate these, let's say, synthesized images of cars. And then because it's a generator, it knows what it does and automatically give them labels. So there's no human
Yep.
involved here. And what we'll do is we'll pre-train the model with those. And what we're learning by doing this, just the synthetic data, no backgrounds or anything else, what are the essential features of what a car
Yeah.
is? Once we've done that, now we take our real world data, we do our full training and fine tune it. The idea here is those weights way down there, we're in the feature extraction, are already kind of locked into just learning essential
Right.
features, and we're just tuning it now. And so we're not learning the data set, we're just fine tuning, learning the essential features so that we can now deploy it in a manner of, of looking at cars we didn't
Yeah.
anticipate and still recognize that's a
That's
car.
very clever. That's a very clever trick. I mean, not everything can be
Okay.
synthesized, but in the ones that can be, that may as
Well,
well.
yeah, there are a lot of more things can.
Absolutely.
Look at all the gaming
Yeah.
engines we have. They're actually most synthetic data today is generated by gaming
Yeah.
engines.
Yeah. With that, I mean, the gaming industry has helped deep learning in so many ways over the years, right? From GPUs and pushing the development of the
Right, right.
hardware, and now the software is also helping drive the field. So that's really cool.
Okay, so we can go to the next
Yeah.
slide. Okay, so here's another
Mm-hmm.
example of feature learning. So occlusion. So let's go back to the example of cars, and you got pedestrians,
Yep.
right? So cause occlusions or ever or a signpost or something, and you still want to recognize it. So again, it comes down to not just essential features, but the model being able to learn how to reconstruct missing parts of those essential
Yeah.
features. Okay. And you don't really want to have to create a data set with a vast number of extra images with people,
Yeah. I mean, it's hard to create.
walking the field and all that. Okay. One way of doing it is different than this is doing the technique called
Mm-hmm.
cutout, which is pretty good. But this is more real world. So you have a separate database of occlusion objects. And you're generating, pulling out your batch, you're just randomly overlaying these occlusion
Gotcha.
objects. And it helps it, learn how to reconstruct essential
Mm-hmm.
features when there are parts
Right.
missing. Now, there's a similar version. I don't even show a slide here. We call it the flying chair version. Okay. So it's a data set of these, say, geometric objects, and it's a well-known data set. One of them are
Okay.
chairs, and it throws them in random locations in the
Okay.
background.
So flying chairs.
and Right, flying
Right.
chairs, right. And it actually helps the model to unlearn the
Oh,
background.
interesting. Yeah, because I was
That's a pre-training task.
gotcha. I was actually thinking about that of just like if you just randomly throw objects to obscure your image, that you could end up in these
Yeah.
kind of interesting situations with, like you said, with the chairs flying. So what do you mean by it helps unlearn the kind of background? Like how does it do that?
Well, it adds. Okay, so let's go back to this really old historical
Mm-hmm.
case of dogs versus wolves. I think everybody's
Right.
heard of that
Yeah,
data
dogs
set,
versus
right?
wolves.
And all the pictures of wolves were taken during the winter with snow in the
Sure.
background. Okay. And then when they tested the model out, anytime you had a picture of a dog with snow in the background, it would say wolf.
Gotcha.
Well, what did it do? Model learned snow, not what the wolf
Right.
is. So we need to somehow train that
Mm-hmm.
model to ignore the
Yeah.
background. And if there's too much commonality in that background, in the
Right.
pictures, part or all of that background is going to end up part of the essential
Sure.
features. And they're not supposed to be. So by sort of randomizing, adding noise to that background,
Mm.
it decorrelates it from the
Okay. Yeah, I see what
objects.
you mean.
And the more decorrelated, the more it will just simply dissipate during what we call the representational learning part of the
Yeah.
model.
No, that makes sense then. Okay. So
And again, all these things are automatic, all these
mm-hmm.
generators and all
Yeah.
that. So you don't do them.
Yeah, I mean, it's already seeming incredible, right? All the things that we've even just so far talked about, chaining them all together into a end-to-end pipeline or as part of a pipeline would lead to phenomenal results. You just slap it in front of like any machine learning workflow you have, and it just instantly becomes better.
Yeah. Well, that's what we do at Google. At Google. Okay, next slide.
All right, so we got unsupervised pretext tasks.
Okay, so this is I really like pretext
Mm-hmm.
training. It's another version of learning essential features.
Okay.
Okay, so far we talked about using synthetic data and inclusion, but what if you just have your data set? Okay, how do you learn them? Well, what we do is, if you think of a model, you got your bottom of your model, and then it gets to, the end where we get to the bottleneck layer, which we call it the latent space. And that's input to the task learner, like learning image classification. If we tear that off and temporarily replace it with a different task, we call it transformation learning. Okay. And what we do is and this is an unlabeled, unsupervised form of
Mm-hmm.
training. So you take your data set and you do some transformation, automatic transformation to
Okay.
it. And the label is the transformation.
Oh.
So for example, jigsaw. Okay, so that's a really popular one. You take your image and you break it into a 3x3
Uh-huh.
grid. So you got 9
Right.
blocks, right? And you randomly
Okay.
reorganize it. And then the label is automatically generated. It's the reorg, it's the reconstruction, the original
Mm-hmm.
ordering,
Mm-hmm.
right? And so the model has to learn how to reconstruct it,
Wow.
how has to learn the transformation
Right.
function.
So it learns how
Okay.
to solve a jigsaw puzzle, basically, in this case.
Right, right. Learns how
Huh.
to, but in doing so, it strengthens its ability to recognize what the essential features
Right.
are. What was not important to learn for the transformation, and what was important to learn for the transformation. So I've trained it now in this pretext task in an unsupervised manner. So I got
Okay.
strong essential features. I tear off the transformational learning. I put back on my task learning unit, and now I do my full
Okay.
training.
So this is considered like in terms of when this happens, it is a pre-training step.
Right. Right. We haven't even gotten into real full
Yeah.
training yet, have we?
Yeah.
Look how much is already
Right.
automated.
And so this is all getting trained through this first pipeline through transformation learning.
Right.
Gotcha.
Uh-huh.
And so the first thing it learns is to solve that jigsaw puzzle, and then you replace it with this to solve your actual task, the real thing you were trying to do in the first place.
Right. You're training it for.
Very cool. That's another very clever approach. Yeah, this field is just
Right.
flying. Just in terms of all the new developments happening.
Okay. So we can go to the next slide.
So we're up to automatic guided hyperparameter
Okay.
tuning.
Tuning. Yeah, and this these automatic hyperparameter tuning always seems like a mystery to people. They hear the
Yeah.
Bayesian, the RAM. And I think this way I can make it really easy for your audience to understand. Okay. And let's take in the context of random. So I'm going to make random combinations of my
Uh-huh.
hyperparameters. And you might ask yourself, well, if they're random and the parameter space is huge, how could I even find a good
Sure.
combination? Okay. And so let's look at it this way. Let's say we have three parameters: batch size, learning rate, and our learning rate schedule represented by this
Right.
cube
Mm-hmm.
space. And we're going to say that the vast majority of it, the white space, is bad
Right.
combinations, not
Right.
good, right? And very little. And we're going to say these little green spots are just tiny little
Mm-hmm.
areas in there where we have the ideal
Okay.
combinations. And trying to find them randomly would be what? Low
Exactly.
probability, right? But we also know where these green areas are. There's a much bigger surrounding yellow area that's near
Okay.
optimal. And we're far more likely to find them through some kind of random or
Mm-hmm.
Bayesian technique. Okay, so let's start with this. We'll just take in the context of random. Think of it as a beam search. I'm going to take a bunch of different random combinations, and I'm going to do a little pre-testing,
Uh-huh.
right? Pre-training and see what I get. Most of them are gonna fall into that white space, and I'm going to
Right.
prune them.
So we're
Okay.
not gonna
But
train them
some
to
of
the end, is what you're saying. We're gonna is that
okay.
early
Oh yeah,
termination?
a pre-training to find the good
Okay. So it doesn't
hyperparameters.
cost much to
Okay.
do.
Right. But here and there, I'm going to fall into a yellow
Okay.
space. And those are my beams I'm going to work off of. Okay. So when I fall into a yellow space, as I indicate here, the presumption is the green space is nearby.
Right.
So now I'm going to narrow my search
Mm-hmm.
space in just the vicinity and then make random combinations within that and hoping that I'll
Yeah.
fall into the green space. And that's basically how, no matter what algorithm you use, how automatic hyperparameter search is
Gotcha.
working. You're you got these combinations, whatever makes the combinations. You're doing a beam search. You're pruning everything that falls into this dead white space. You're looking to get into those near optimal yellow spaces, wherever those are the beams you
Uh-huh.
keep. And with them, you narrow the search space, and then you'll reapply the algorithm within that in hopes of finding that good green space.
Awesome. So Andy, would it be helpful for viewers to talk a little bit more about kind of what you mean by the term beam search, just so we're specific, because beam can be interpreted a number of different ways. Yeah.
Okay, yeah, it's just a basic AI concept. Is when you do, it's kind of like you don't like a black box
Mm-hmm.
search. You don't know, you can't see past the
Yeah.
wall, the
Right.
box, right? So you can't make educated guesses. Okay. So instead, what you do is you make a bunch of parallel
Uh-huh.
tries through the box, right? And you get some
Right.
feedback. And based on that feedback, you decide which of those parallel tries were good starts and which ones weren't. Those are your beams. And the ones you decide weren't good, you
Uh-huh.
prune.
Okay, so
And then
the
you take
term
the
beam
red
is
one.
just a way to characterize the process we described. Oh, okay.
Right,
Okay,
right.
I hadn't heard the
Right.
term.
And
That
it
was the
comes
thing.
from the old AIJs. Okay. And then you take the ones that you think are good and then you make new guesses of how to improve them.
Yep.
And you fire those off in parallel. Those are your new beams. You get the
Mm-hmm.
feedback,
Mm-hmm.
right? And you apply the same process. The ones that didn't turn out to be good, you prune, and the other ones that
Yeah.
show promise, you keep them, and then you can just repetitively repeat the
Do
process.
you have any thoughts on why it's called that by any chance? Where the name comes from?
Um, Yeah, it's beam is like you're like your flashlight or
Uh-huh.
light. You're beaming it. You're making a beam into you're shining light into a black
Yeah.
box.
Fair enough.
So it's light beam. It comes from the phrase
Yeah.
light beam.
Cool. A comment on the live stream is that this seems a little bit similar to in process to the search of the initialization weights, in that we're kind of trying a bunch of things and then picking the ones that are good. And I guess in that case, we just picked one time, whereas here we are progressing
Yeah,
further.
yeah. I mean, they're all different, different types of search
Yeah.
algorithms. based on some
Mm-hmm.
randomness. So yeah, all these types of automatic search algorithms are rooted in some initial step that's assumed
Yeah,
to be
yeah, and
random.
then there's bound to be some overlap in the concepts that are adopted here. So now we're on to knowledge distillation.
Okay, so this is about how to train what we call a compact
Mm-hmm.
model. And many of your viewers have probably heard of the teacher student model. And what does that mean? Okay. Well, today, when we train what we call large models that have high accuracy, the reason they do is because they have what we call
Mm,
overcapacity. They have a lot of
right.
redundancy, and that all that redundancy helps in the accuracy. But you can't put those large models on a mobile device or an IoT that's
Exactly.
memory controlled. And what we have found is if we make a tiny model without all that overcapacity and directly train it, we don't get that good
Right.
accuracy.
It's
It's
really
really
hard to,
hard.
yeah, pull that off.
So the concept of knowledge distillation is use the large
Mm-hmm.
model to train the little model instead of the data set.
Huh.
Okay, so just to simplify how it works is, so I got this pre-trained large model. That's my teacher, is very high
Right.
accuracy. Okay, and if you think what comes out of it is a probability
Right.
distribution, it's not really let's think of its fruit, apples, pears, oranges. It's not going to say one for apple and zero for the other one. It's going to say 0.97
Mm-hmm.
apple, right? 0.02 pear, zero point zero 0.01
Yep.
orange. And those are called soft labels, the actual probability
Yeah.
distribution. And I'm going to use those soft labels as the labels, not the hard labels, the ground truths, as what I'm going to train the compact
Oh,
model
interesting.
through. So let's start simple. I take my training data,
Mm-hmm.
right? Okay, and I'm going to run it through the two models in parallel. So a copy that goes through the pre-trained model, and I get a probability distribution. And then a copy that goes through the compact model, and it gets a probability
Right.
distribution. And my loss function is going to be between the probability
Right. It's going to be
distribution.
the
I'm going
difference
to
between
train
those two.
the compact model to minimize that loss such that it mimics the probability
Right.
distribution of the large
Right.
model. So it's not learning the data, it's learning the large model's probability distribution on that
Yeah.
data.
Interesting. So we're trying to minimize the difference between the softmax outputs of the large model and the compact
Yeah,
model.
exactly.
Interesting. And this achieves the goal. This somehow leads to the student model being able to recognize the data accurately.
More accurately than if it was just trained on the training data
Interesting.
without the assistance of the
Why do
teacher.
you think? Why do folks think that is? Like, how do they think it works in terms of like why is it effective?
Um,
Do you have any thoughts on that?
well, it probably helps it to better
Yeah.
generalize. If you think about hard
Yeah. It's
labels,
it's
they're
one
ones
and
and
zero.
zeros, right?
Yeah.
Right. And you're trying to force that little model that doesn't have a lot of
Mm-hmm.
nodes to try to get to ones and
Yeah.
zeros, and it just doesn't have enough capacity. It's probably easier to train it to get to 0.68 and
Uh huh.
0.97 and 0.89. But then what you want those is not, and that's probably what would happen anyways if you directly train it with training data, but that might not be the correct
Yeah.
distribution to get the same
Right. Okay.
accuracy, the large one. So let's just train it on that distribution of the large one.
Yeah. That's really neat. It's a very clever technique for sure. All right. So on
Okay.
to
So
we
next
got data denoising via weekly
Okay,
supervision.
so
Weak supervision.
so we're going to cover a little briefly talk about things like weekly supervised learning and self-supervised
Mm-hmm.
learning. Again, they fall into automatic
Yeah. And
learning.
Andy,
So weekly
Andy, before
supervised,
we go on, a quick question on the previous one from the live chat about how this method is different or similar to pruning and dropout, right? Pruning where we are removing cells, and then dropout where they're randomly deactivated for a certain training batch.
okay, so so that sort of falls into the area of model
Uh huh.
compression. So we've trained a large model and we now want to compress it.
Yeah.
Okay. And so we're going to look for things like sparsity. So nodes that have tiny values really close to zero aren't really contributing
Right. So that's
anything.
pruning.
So we can just drop
Mm-hmm.
them. Okay. Clusters of nodes whose weights are very close to each other effectively are symmetry, and we can reduce them down to a
Right.
single node.
Yeah, that makes sense. And I guess the difference with those processes and what is happening here, oh, I see. Well, is mainly because we're trained. This is kind of a method around how we're performing the training with a model that is initialized to a small size rather than taking a large model and trying to shrink it in stepwise fashion, through these different
Into
techniques.
a
Yeah.
small model.
Cool. So hopefully that answers that question. Yeah, and so I guess now we're talking about weakly supervised data denoising.
So when we're talking about weakly supervised data, we're talking about training on noisy
Mm-hmm.
data. And the reason we call it weakly supervised is because we're going to use weak learners. Okay, so let me describe it here. So let's say you have some good labeled data, but you don't have a lot of
Okay.
it. Okay, but you have access to a vast amount of other data that may not be labeled all that well. For example, it may be
Sure.
crowdsourced from different people,
Yeah.
right? And everybody has a different perspective of what a car is or what a car is, or even how they put the label car in. So it's a little bit noisy. Or you got some automatic program that does a search on the internet and pulls down all these images,
Right.
right? Well, 10% of them really aren't. You say Apple, and you're 10% of them, are you're going to get an Apple cell phone or
Yeah.
something,
Yeah.
right? Okay, so there's always some noise when you get data from those sources. And the idea is, well, how can I use that noisy data? You really don't want to train on it as is. It's just a little too noisy. And so in weakly supervised training, the goal is to make it a little less noisy. Okay, so we're gonna use the ensemble
Uh huh.
method. Okay, we're gonna train a bunch of little models. And in ensemble, what makes ensemble works, it really goes back to the 1700s, those mathematical principle relating to actually juries. The assumption that if everybody made a good guess, that means they were right at more than 50% of
Uh
the
huh.
time, the more people you add, the more
Right.
accurate getting the right
Right.
answer. Okay. And then that was the foundation of juries. Okay. And that's called an ensemble. So I'm going to train all these weak learners, and I'm going to start training them with the noisy data. We really don't know how accurate they're going to be. But then I'm going to turn around and sort of button them up, get them a little bit better with the labeled
Okay.
data. So fine tune it. So the assumption is every one of these weak learners is a little bit better than
Yeah.
50%. Okay, but I got a bunch of them, and each one is slightly little different. And of course, I can then use the majority voting
Exactly.
system. So let's go to the next slide where I'll show you part two. I couldn't get it all on one slide. Okay, so now I have these weakly trained ensemble, and I start over again. I run the noisy data through it, and the assumption is I got less noisy
Right.
data. It's of a better, it's not
Uh huh.
clean, but it's of a better good enough that when I combine it with the labeled data, it's good enough and I can train a strong model.
Gotcha. Interesting.
And of course, what the ensemble does here is it's basically going to use majority
Mm-hmm.
voting. Okay, so I put something through, and two say it's an apple, one says it's a pear. It's just going to say it's
Right.
an
And so
apple.
it'll basically relabel the data where needed to kind of fix some of that noise for us.
Right. Just trying to remove
Mm-hmm.
some of the noise out.
And I might have missed this, but how are we training each of these different learners? Are they different models? Are they seeing different portions of the data set?
Now they're usually the same model
Uh huh.
instance. Okay. They just have a different random
Oh, okay,
draw.
just a different initialization. That's it. Wow.
Usually enough, just enough. So they're not going to be
Yeah,
substantially
that's very
different.
similar.
The differences between them are going to be
Mm-hmm.
minor, but just enough to give you a little, you say, distribution and best
Yeah.
opinion.
Okay. Okay.
Like having a room full of experts. They're all going to make a good
Uh huh.
statement, right? Okay. But there's still going to
Some
be some
differences.
variation,
Yeah. Okay.
right? and we're just trying to get sort of the mean of that variation.
And what is it that makes this learner weak? Is it the data, the duration of
Oh yes,
training? It's just the data.
we call it a weak learner that isn't. Okay. We have strong learner and weak learner. So when we think of training a model to get high accuracy, that's a strong learner. It's highly accurate. Okay. If you drop the accuracy down to the ensemble concept, it's always at least 50% accurate, but I don't guarantee anything more. We call that a
Gotcha.
learner.
Okay, so it's just like
If I
weaker.
model, the more weak learners I put in a room, the more and more likely, if I do majority voting, I'm going to get the right answer.
So it's just like a weaker guarantee, only 50% or more. Cool. Yeah. On to data labeling via self-supervised approaches.
Yeah, so there's a wide variety of self-supervised learning. Okay, I'm only going to discuss one of them here. But in effect, it's all about I'm going to learn with unlabeled data.
Right. Okay.
Now, this is unsupervised learning where you're doing clustering. So self-supervised, the goal of self-supervised data is there a way to take unlabeled data and get it labeled? Now, so let's start off. We already have a pre-trained model that's pretty good in accuracy to start with.
And that model is trained on which data set?
Unlabeled data. Good labeled data. Okay, so let's go back to the scenario. I got an existing data set. It's good labeled, but it's not a big one.
Okay.
So I train the model, right? And the model does a good job on it, but it's not enough to really generalize and get high accuracy. And I have access to a vast trove of other data, but it's all unlabeled. And I don't pay or take the time to get it labeled. Okay. Well, the assumption is I can take all that labeled data and run it through the model the first time and just have the model predict what it thinks the label would be.
And that's this guy.
Right. We call it the pseudo labeled data. Okay. You don't really know what the accuracy the accuracy distribution is going to be no more better than the accuracy distribution of the trained model, right? And so the trained model is only 70% accurate. As probable label distribution is only 70% right.
So,
but now what I'm going to do is I'm going to take that 70% right set of data and combine it with my good label data. That's 100, which makes it a stronger combination. Okay. I call that my composite training data, and I'm going to spin it around and pass it through the model again. This is the assumption the next time it comes through the model gets a little more accurate. Let's say it's 72.
It'll improve the pseudo labeled data.
Right, along with the good data. And this time, the next time it generates pseudo labeled data, its distribution may go up a little bit. Now it's like 73%. I just keep repeating this cycle, trying to pump up the distribution accuracy of my pseudo labeled data.
That's very clever.
And that's training. No humans involved. Nobody is no human annotator is involved.
Interesting. And of course, which individual items of data, like each row, for instance, if they came originally from that labeled data set, or if they originally came, because you wouldn't want to change the labeled data after it's been dumped in this pile and then it gets messed up.
The old cassette tape where the little clip is broken off, you can't over.
Yes, that's right. No overwriting the good data. Very cool.
Yeah, let's go to the next slide.
So we're on to some data validation techniques.
This one's a little complex to grasp. The concept here is, given a data set, some of your examples contribute more to the model than others.
Right.
Okay. And what you would like to know is that distribution. And let's just keep it simple, a hierarchy. Really good, okay, not so good. And what we have found in research that in a data set, if you could take those low end ones, the not so good ones, and actually take them out of the data set, you'll train a better model.
Yeah. Yeah. Take.
Now, it doesn't mean those not so good ones are noisy. They may be, it really is what it is, and the label's really correct. But for some reason, it doesn't contribute well to the training of the model, or even may
Yeah.
distract from it in the wrong direction. Okay. So the question is, how do we find the not so good
Yeah.
ones? And so data validation using reinforcement learning. Okay. So you have actually you work with two models. So you have your predictor model, the one you're trying to
Uh
train.
huh.
Okay. You have your data value estimator, which is really a reinforcement learning
Okay.
model. Okay. And so you take your training data, and it's going to start off, let's say, with a random hypothesis of how each example is going to contribute.
Right.
Okay. And you then send it to the predictor model, that batch, and you see how those examples did or did not
Uh huh.
improve the model. And that, if you think of reinforcement learning, that's your reward function
Right.
that gets passed back to the data value estimator that updates its policy, reweights them based on it, send them back through again. The examples come out. You look at how well they did or did not contribute. That's your reward function. Do enough iterations, you get a policy, you learn a policy to accurately estimate on each example which the level they contribute. And once you do that, you can now prune your data
Right.
set.
Now, with this model, each time through, are we retraining the model from scratch again, or are we doing one epoch? Are we doing one training step? Like, how much is happening at this stage?
We're not retraining it
Uh
from
huh.
scratch. We're doing this in
Okay.
parallel. Okay? So, and you'll see, the batches are small. I mean, in theory, you could do it one element at a time. That would be the ideal way, but
Interesting.
that takes the
Right.
longest. Okay. Right. So we take small batches,
Right.
maybe 8 or 16. So we're going to treat them all with the same reward function,
Right.
even though they contributed
Yeah, because the
differently.
model is going to be changing.
Right. But because with every
Uh huh.
epoch, you get a new batch distribution. They show up in different batches. So it learns eventually to, disentangle
Yeah.
that. Okay. And yeah, I mean, the first few times around, the model is a poor predictor. And so that reward function is kind of
Yes. I
meaningless,
mean, yeah,
right?
reinforcement learning is famously difficult to kind
Right.
of
Right.
bootstrap.
But as you build up the model, as it gets more and more accurate, more and more meaningful reward
Yeah.
function, you've also had the benefit of, while you're getting up there, of sort of developing the policy, the likely policy. So you're learning these two things in
Yeah.
conjunction.
A question from Skander Hanachi here. Is this just the idea behind a neuroarchitecture search applied
Oh,
to
no.
data validation as opposed to applying it to kind of the main training part, right? Like,
I would say no. And we have a slide on a neural
yeah,
structured cert.
cool. Macro architecture. Yeah,
Oh.
speaking of which,
Oh, good. Hey, what happened there? Okay, so this kind of gets to the network architecture search
mm-hmm,
NAS, but there's actually two levels of it. One is
mm-hmm,
macro and one is
right,
micro.
right,
So those original papers, like on NASNet and then AmoebaNet and even on EfficientNet, are all done what we call micro architecture search, which is highly expensive
okay,
computationally. Okay. There's a much lesser form of it, substantially less expensive, called macro architecture
mm-hmm,
search, which is much more commonly used because it's more computationally effective for
great.
people. And matter of fact, MobileNet v3 was discovered using macro
Oh, no
architecture
kidding.
search. So, okay, so here's how the concept works. Okay, so you got some search, you got something that functions here on the left box. It's the search space in the training, and you're going to give it to it the sort of specs, this guided search space. Here's sort of the real whole world to search inside of to find the best
Yeah,
architecture. Okay, and it's going to, it starts off random. I'm going to think there's a loop based on what's happened. It wants to improve, like yes. But what it's going to design is not the fine details, but the component connections. So it's going to be connected to what we call a factory. So if those of you who are familiar with OOP, this is the factory design pattern. Okay. And it'll be specific to an architecture like ResNet. Okay. So all the inner components are all identical. We don't change them, the connectivity and things like that, but how they hook together and lock assemblies.
Uh-oh.
That's
our internet is a little
the search space is really giving it a requirement to the factory design pattern.
Yeah, the Wi-Fi seems to be
on the feedback search space, makes a decision on the next requirements to give to the factory pattern.
Hey, Andy? We had a little bit of dropout on connectivity there just for the last kind of 10 or 15 seconds. Do you mind repeating just that last bit you covered around kind of these final bits around after the factory pattern?
Okay, yeah, I'll just summarize it. So the search space is going to come up with some requirements based on what it's seen so far. Each time it's trying to improve on the requirements, narrow in on a better and better model. And those requirements go into that factory pattern. That's specific to a model architecture. It reads those requirements and creates, it's a factory, creates that macro architecture for that architecture specific one. That gives you the model instance, and then we train on it. Take the feedback, and then the search space driver makes a decision based on all this accumulated feedback, how to improve those requirements, and then resubmits it back to the factory, and you just keep doing this.
So in a lot of ways, this is possibly what I think a lot of us think of when we think about neuroarchitecture search in kind of the classic sense of like trying to find network structure. And it sounds like we're specifically here talking about large structural patterns where we have repeated. Awesome.
Okay. So we'll go next into microarchitecture search. Okay. So here we're not assembling from an architecture specific factory like a ResNet or a DesNet or something like that. Instead, we're going to work with, again, OOP people would be familiar with, an abstract factory pattern. And from an abstract factory pattern, it produces a factory pattern from which we can then create macro architectures. So you have the same sort of thing. You start with this guided search space settings, this big course level thing. The search space again hasn't really changed. It's still making group and block recommendations. But now it goes to the abstract factory pattern. And based on the past, what it's learned so far, it'll make decisions of what architecture specific one to use, or what changes to make to that architecture specific, even conceive a new architecture that's a mild derivative of other architectures, like a ResNet plus, let's say. That creates then a factory pattern.
So that's
and
coming
now
from
your
here.
group requirements go to the factory pattern, and you're back to the macro architecture.
So that's kind of going from this one here into this one. To that, this is kind of the extra thing.
Really the only difference. That additional step is hyper expensive.
It's funny how like sometimes you take one thing and then it's like let me add this one thing, and all of a sudden everything is like way.
I mean, that thing isn't actually trying to find a model that's better. It's trying to find a factory pattern
that's better. Whoa.
That's better.
So meta.
And then you tune it with the macro architecture search.
All right. Unseen covariant surrogate approach.
Okay, so this is how, and this is 2 slides here. We'll start with the first one. So this is like dealing with bias in your data set. So, people are all familiar with this term, in certain areas, historically gender was a bias, like maybe getting a loan, okay? And so people try, what if I just take that column out, anything that implies the gender? and train on it. What we find in general, that doesn't work. Okay, because there's some other thing that is
Yeah.
correlated with the gender in there, acts as a proxy or what we call a
Right.
covariant.
Ah,
Okay,
so
so the
it's an
first step
unseen
is
covariant.
the
Okay.
unseen covariant. Okay, so but let's take our original data set and let's say it does have the gender
Uh-huh.
in it, and we want to know, does or does not the gender bias the model? So what we do is we're going to work with what we call a surrogate model that we're going to train to see if there is a
Okay.
bias. So this isn't the model that we're going to train to make a prediction, but one to train, is there a bias? First, we need to know, is there a
Right.
bias?
So this is our surrogate model that
Okay.
we're training here.
Right. Okay. So basically, that target model, you take your training data and you're gonna remove the bias from it, so you can see the next training data without the
Right.
bias, and you're going to run it through the regressor. Okay, and it's going to make some kind of
Uh-huh.
prediction. And well, that's actually the real model. The regressor is the real
Right.
model. Okay, and then its output is going to go to a second model, a surrogate. It's a logistic, a binary classifier. It's going to say yes or
Uh-huh.
no. And the label is the bias.
Oh.
And we want to see if it can predict the bias or not. If the output of the regressor is correlated with the bias we removed.
Uh-huh.
Okay. If there's no I bias, it should be random. It wouldn't know. Our accuracy of the logistic should be only about 50%. It's kind of like that adversarial type of thing.
Yeah.
Okay.
Bias
Okay. So if
feature.
I get 50%, there's no bias. I don't worry about it. If I get something that's more than 50%, I got a problem. It's a
Right.
bias. So let's now go to the next step, assuming it is a bias. Okay, so I'm going to use a form of adversarial
Uh-huh.
training to drive the bias out. So I take that training data, go back to the original training data with the bias,
Right.
right? And I'm going to go two different paths. So through the train model, the regressor, I'm going to give it the training data without the bias. Now we know that there's some unseen
Mm-hmm.
covariant in there. It's still somehow reflected in it
Yeah.
in the
But we got to
predicted
find it
score
somehow.
coming out. Okay. All right. Now to the other model, the logistic one, I'm going to reuse it now because I've already trained
Right.
it on the first step. Okay. I'm going to give it the same thing, but I'm going to flip the
Okay.
bias. So whatever it is. So if it was male, it's going to say female. If it was female, it's going to say
Uh-huh.
male, right? So I got what I call the inverted bias and the score coming here. And my loss function is between the two. So I'm being adversarial. I'm intentionally telling it the opposite each time on the
Yeah.
unseen covariant, forcing it to sort of unlearn it in an
Yeah.
adversarial
And so
manner.
the final loss is these two losses combined? Okay.
Right.
So it says here min max, minimax loss adverse.
Yeah, it's a mini type of adversarial. One is trying to maximize, one is trying to
Oh, right, right.
minimize.
So it's kind of two losses to optimize for, just in the opposite
Right.
directions.
Mhm.
Very cool. That's a really neat approach, and again the very kind of clever um, wiring, right, of the flow of data and where you stick a model to detect certain things, and in this case, trick that model almost.
Yeah, yeah. Well, that's what adversarial training is about. You're tricking them. That's a
Yeah.
good phrase. You're tricking the model. Okay, neural learning. I
Yes.
think that's what one of your viewers brought
Mm-hmm.
up. Okay. Um, so what this is, let me let me start this way. It's a training method, but it actually has a task within a
Okay.
task, and that task within a task is actually a pretext task, like we talked about earlier. But remember, we did that as a warm up
Right.
pre-training, and then we did the full training. Now we're going to put it inside the model and train it in parallel.
Okay.
Okay. And here's how we do it. And of course, the purpose is to learn the essential
Right.
features, not the
Right.
data. So now we're ready to train, and we take a batch from our
Mm-hmm.
data. And let's say it's some data. We got 16 of them in there. And then we're going to make a copy of that batch. So it's going to have 16. And it's going to be what we call almost identical to the first
Okay.
one, but just some slight variance.
Right.
And usually we're going to do some random notation to it, like the translational scale
Yeah.
invariance. We might rotate it or flip it or
So
something.
that's this red
Okay.
box down
Now,
here. Okay.
right. Now, if our model was truly generalized to the real world and handled data drift, then those two batches on their prediction should be identical,
Sure.
right?
Yeah. Yeah.
100%. So now we run the two batches parallel through the
Yep.
model. So now we got 32
Mm-hmm.
examples, 16 each. So you come out to the other end of the model to what we call the bottleneck
Yeah.
layer before you go into the task learner. So you split them. So here's the original batch. Here's my perpetuated
Yeah.
batch. Each one of them then goes through their task
Uh-huh.
learning in parallel, identical task learning task. Again, this says classification. Okay. And they output. Now, in theory, if my model was 100% generalized, those would be identical. So that's what that L2 loss is there.
Yeah.
So if they were exactly identical, that would be
Uh-huh.
0. The more and more they're further away, that's a penalty
Yes.
I'm going to add to the loss function on training
Uh-huh.
the model itself and its output. So I'm training it to do two things in parallel. One, learn to correctly, let's say, classify these images. And at the second time, learn just to look at the essential features by adding this
Mm-hmm.
penalty inside of the model. It's also referred to as batch regularization. So you got weight decay, weight regularizations, all different
Right.
types of regularization.
Yeah.
So that's just a name for it.
Because and for folks who aren't familiar with the term regularization, right, we're trying to regularize or reduce the noise, kind of reduce the difference. And so in this particular case, what's really clever here is because we've separated these two data sets, we've marked them as being the original true batch and then the randomly perturbed batch. We can then calculate this penalty and compute this L2 loss, which is used, right? Whereas I feel like kind of traditionally, so to speak, you can say, oh, I've augmented my data set, but then it's just a random draw, and you don't have this direct comparison of saying, not only do I want the overall accuracy to be good, but I specifically want the difference between this half and this half to be small. And it's like a
Right.
subtle difference, but it really gets to the heart of the matter in a way.
Right, and it helps speed up training. So if you go back to when I talked about the pre-test
Uh-huh.
task training, like with the jigsaw puzzle, to learn the essential
Right.
features. So that's one training cycle, and then I had my full training cycle where now I use the actual ground truths to fine tune it. Here, those two tasks are happening at the
Yeah.
same time.
So you don't have to, they're in parallel instead of in serial, which is nice.
Right, which is really what neural structured learning is about.
Cool.
I put the pretext task inside as part of the model.
How are we doing in terms of, I'm not 100% sure how many more you've got lined up for us?
Last slide. The highest mark frontier.
Oh, how exciting. We're getting there. We're getting there. All right.
We're there. So I'm going to spend much on this. So today we work on what we call model amalgamations. And it kind of just means that the model is the whole application now, or models.
Okay.
So if you go back a little bit in time, yes, we wrote applications that use a polarity of models, but we tended to have those models sort of each be an island with some kind of REST interface, and then you had some back-end application like a Java application that would make calls out to those individual models. Well, today now we hook models together with each other, and and there are different points. We don't think of a model anymore as having a single output. Sometimes the hard labels are output. Sometimes it's the soft labels. Sometimes it's the bottleneck layer. Sometimes it's the feature vector. And so we can connect them in different ways and sort of make composition as the whole application. But the thing is, once you get to this level of complexity, finding that best connection point between two models and how in the communication path between them, again, that's a human engineered thing, but we've discovered that can be machine designed too. So that's sort of where we're working now. Right now we're still, us as engineers, building by hand these model amalgamations, but we see the next forefront in automatic learning, having tools that actually learn the best way, the best interfaces and connections between these models.
That is amazing. I mean,
and that's the world of automatic learning today.
Yeah, that is an awesome whirlwind tour of kind of all these techniques. And I'm so glad we were able to go into kind of such depth about the process and the details around how these are implemented, because this will help viewers and future viewers too of this video be able to kind of explore more and use some of these words and keywords to search and learn more and get deeper into the topics that are relevant to them. And moreover, it seems like they're not necessarily kind of overlapping too much, to the extent that you're able to chain them together and apply much of these techniques to all at once in a manner of speaking, to any kind of machine learning application or training task. Yeah. So I want to be sensitive to your time, but thanks so much for joining us, Andrew, and everybody on the live stream. As always, thank you for your questions and your participation. That this kind of wraps up this week of live streams. Next week we've got a couple of different things planned. Concretely, it's still the usual Monday, Wednesday, Friday at 3 p.m. Eastern, noon Pacific schedule. We'll have on Wednesday, my colleague Tahir from London will be joining us to talk about some open analytics approaches in terms of doing data manipulations in Spark and Hadoop. So for those of you who or have friends who are interested in those kinds of areas and running Jupyter notebooks on top of a Spark cluster to launch jobs and things like that, we'll be digging into how to set that up, kick off those jobs, and visualize your data sets and make kind of a nice data flow setup and visualization within Google Cloud. So really looking forward to that. And I think on the other days, our general plan is we'll continue building out some of the kind of application layers that we've been working on. I think most of our data set munging is complete. And so next week, what I'm excited to do is dive more into the ML side of things, more into the machine learning side of things. Andrew, just to give you context, I've been setting up a data streaming system for the Open Images data set, which I think is now at V6. Okay. So we have like, a terabyte of images loaded onto a persistent disk. It's like 1.7 million images, right? So I was like downloading these like half terabyte.
Like you need that validation method to figure out which one is useful.
Yeah, so these things this is going to be super relevant, and I'm really excited for that. Getting to these interesting steps, because I have a data set now that's large enough, and some of which is like poorly labeled enough that it actually would help improve things, especially that idea of kind of the pseudo labels and spinning it through.
Yeah, the self-supervised.
Yeah, the what is it? Self-supervised.
Self-supervised learning.
And because I know that data set, they mark kind of that some of the data is really human labeled, and then they actually do have some machine labeled data. So we do kind of have that mix of like really good data labeling and then kind of okay labeled data. Yeah, and yeah, people are saying thanks on the live stream, and yeah, thank you, Andrew, for joining us today. This was super interesting, and yeah, with that, I think we'll call it there and wrap it up. Have a great weekend, everybody. Okay. Be well, be safe, and we'll catch you next week.